Okay, so this is question 10 in sample exam 3 in Chem 11. This question is about electronic transition in the hydrogen atom, which is referring to that concept of the Bohr model, the one electron model, where you have a nucleus in the middle and you have your orbits where the electrons could be found in. And this one specifically is asking about a transition from the 6d orbital to the 4p orbital. Now, if you remember in the hydrogen atom or anything that has one electron in them, we use this Bohr equation, which really looks like this, right? That the energy change that occurs when the electron moves from one orbit to the other can be calculated by taking a constant, which is called the Rydberg constant, times 1 over n final squared minus 1 over n initial squared, where n here refers to the orbit values, which we call the Bohr orbit values or energy levels. Now, when quantum mechanics come around, we redefine or repurpose this n from the Bohr model and call it the principal quantum number instead. Okay, and so those two are referring to the same thing, which is this n. The n in the Bohr model is this thing he calls the orbit, where the electrons can be found. Later on, it was discovered that the Bohr model is not quite right, doesn't really work for anything bigger than one electron. So when quantum mechanics come around, they still have that number, but they call it the principal quantum number. So if you look at the question, it's asking to figure out what the energy of the photon that would come out in the form of the frequency of the photon when there's a transition from 6d to 4p. Now 6d to 4p, of course, is using quantum mechanical concepts here, because in the Bohr model there isn't a 6d or a 4p orbital. It's just orbit value, either 1, 2, 3, 4, etc. If you look at the formula to calculate the energy transition, notice that it just depends on the value of n. It doesn't really depend on the type of orbital. So if you look at 6d, for example, if you look at the way that an orbital is labeled, when you say 6d, there's two numbers here, right? One is n, which is the principal quantum number, and the other one is L, which is the angular momentum quantum number. But in the equation to calculate energy, the only number that matters is the principal quantum number. So really, whether it's going from 6d or 6s or 6p to 4p, it really doesn't matter. What we can say is that what we're asking for is a transition from 6 to 4, because those are the only two numbers that matter for one electron system like the hydrogen atom. So what we can do is we can calculate that energy transition by taking the Rydberg constant, which is this value, times, it goes from 6 to 4, so 4 is the final, 6 is the initial, and when you calculate that, you get negative 7.56 times 10 to the minus 20 joule. The negative here refers to the release of energy, right? So not necessarily anything mathematical, just releasing energy as the electron falls from a higher to a lower orbit. And then the next thing you need to do is then you say, well, the delta E, the energy that's released, is going to be the same as the energy of the photon that's emitted. And the energy of a photon is h nu, or hc over lambda. In this case, we're trying to find frequency, so we can just say that the energy of photon will be 7.56 times 10 to the minus 20th joule. That's equals to h nu. Now, why is the negative sign that I highlighted earlier disappear in this case? Well, the idea is that you can think of this as the electron is releasing energy and the photon is absorbing that energy. Now, of course, the photon is also being emitted at the same time, but there's, if you look at it from a thermodynamics perspective, one system is releasing energy, the other one's absorbing energy. So as a result, I can use this to calculate nu, with nu being this over Planck's constant, and the joules cancel out, and your final answer is going to be 1.14 times 10 to the 14 per second, or the same as hertz. And so looking back at the answer, that would correspond to A.